Rod and rails. We have a conducting rod of mass m and length L down here. It moves on top of two frictionless horizontal rails, shown this way, that are connected to a battery that maintains a constant current I in the circuit with negligible resistance. So we're going to have a battery over there. The circuit is placed within an upward uniform magnetic field B. Find the direction and magnitude of the net force on the rod. Determine the speed of the rod as a function of time. Find the distance that the rod moves from rest to reach a speed v. Now we have friction between the rod and the rails with the coefficient of friction mu. Find the new distance that the rod must move in order to attain the same speed v found in part C. Find the direction and magnitude of the net force on the rod. And you can see the current going through the rod here, so that must mean we have a battery here perhaps. Use the right-hand rule to find that the direction of the magnetic force is to the right. Okay, so if I take my right hand and I put the four fingers in the direction of the current, and I face the palm of my hand upwards, because that's the direction of the magnetic field, hopefully your thumb, when you extend it, points to the right. So the direction of the net force will be to the right, and the magnitude, right, it's IL, we'll just do the vector part, IL cross B. But the direction of the current is perpendicular to the magnetic field, so to find the magnitude, that'll be ILB sine theta. The sine of 90 is 1. So here we go. That's the answer. All letters because they didn't give us any numbers here. Determine the speed of the rod as a function of time. We need acceleration to find speed or velocity, so we will find the acceleration of the rod due to the magnetic force, and once we have that, we'll use the first kinematics equation with our initial velocity equal to 0. Kinematics, again, never goes away. So here we are doing magnetism, and we're back to where we started when we first started the course. So we have our force, it's ILB, which is equal to MA, so the acceleration of the rod is ILB over M. Here's our first kinematics equation. We have a 0 initial velocity, so that goes away. And velocity at any time will be ILBT over M. Find the distance that the rod moves from rest to reach speed v. We're going to use the third kinematics equation. And why is that? We don't need time in this. They're not asking about time, but they want a final speed v. The initial speed v is 0, and we want a distance, and we know what the acceleration is, so third kinematics works perfectly. Do a little rearranging. We have the distance, or the displacement, as v squared over 2a. We substitute our value in for a, then we clean up the equation, and this is what we get, mv squared over 2ILB. There is now friction between the rod and the rails with the coefficient of friction mu. Find the new distance that the rod must move in order to attain the same speed v. You imagine it'll be a greater distance. Why? Because you now have a force acting against you. And our net force is going to be reduced by the friction force. Friction force is mu times normal, and in this case, since the rod is not accelerating in the up direction at all, normal is just mg, so the friction force will be mu mg. We have Newton's second law, the sum of the forces over m equals acceleration. We've added the negative friction force here. Once again, we go to the third kinematics equation. We substitute in for a, and we do some rearrangement and come up with this answer. Let's just check the units real quick. What do we have on the left side? Well, that's a distance. I'll put it up here, distance. And on the right side, in the numerator, we have energy, right? mv squared, you can bring the 2 up there. We don't really worry about that. We're just looking for units. So you have energy. And then what happens? What's this denominator here? That's a force. So let's bring that over here. And we have force times distance equals energy. Well, force times distance is work. Work equals energy. Again, we're just talking about units here. So it looks like this fits that quite well.